Welcome to the first pilot episode of marktroyer.tech. Today we'll investigate how to build an ESP8266 based project without any software development. We'll be using the Tasmota open source firmware project. This is my first YouTube video and what I hope will be a fun series focused on learning, mastering, and applying technology. Today we're working to get a better understanding of Tasmota. If you're not familiar with Tasmota, it's an open source project designed for the Espressif line of microprocessors. This includes the ESP8266 and the ESP32 microprocessors. Its purpose is to provide an open home automation functionality on readily available IoT consumer products. For example, on the bench, I have 3 relay switches, a Sonoff Basic, a Sonoff S20, and a Shelly 1 switch. All of these products are based on the ESP8266, and all of these products have the Tasmota firmware loaded. Once Tasmota is uploaded, the device can be managed either through a web page interface or through an MQTT broker or even a web service call. For example, this is the Tasmota web interface for the Sonoff Basic module. This is where I do the initial setup to configure the device. Tasmota can be part of a large IoT home automation project, or it can be used standalone without an internet connection. Personally, I'm using Tasmota on a Sonoff Basic for 3 standalone use cases. The first saves energy and prevents potential fires as a result of my sometimes forgetful nature. In this case, I've connected a Sonoff Basic between the mains power and my office space heater. This way, I never forget to turn it off. The Sonoff has been configured to stay on for 120 minutes after I press the switch, and then it turns off automatically. There's no outside connectivity per se, as I did not see the need for an IoT office heater. I've also configured a Sonoff Basic in a similar configuration for both my soldering iron and my electric blanket. They both turn off automatically, and I can rest assured that there is no wasted energy or fire danger. I find Tasmota firmware compelling as it seems to be able to satisfy 80% of my use case needs without having to program any code. In a large number of cases, I can use Tasmota with off-the-shelf switches, lights, motion sensors, thermostats, and many other sensor types. In other cases, I can build custom devices without the need for writing any firmware, whether it be in Arduino, MicroPython, or any other development environment. With Tasmota, most use cases can simply be configured without programming. Today we're going to walk through 3 configuration exercises with Tasmota. First, we'll build a breadboard device that mimics a Sonoff Basic. We'll be using a WeMOS D1 Mini and several parts to do this. Once we've completed this, we'll then clear out all of the configuration on the D1 Mini, and then we'll manually reconfigure everything to show you how this would be done for any type of device that you might want to make. Finally, in the third exercise, we'll build a reference PCB for testing and learning Tasmota. It'll also be useful for other home automation projects as it has several components on the board. That includes, as an example, a temperature sensor, a light sensor, a couple of momentary push buttons, a buzzer, as well as several LEDs. So let's go ahead and get started with the first exercise where we're going to mimic the functionality on the breadboard of the Sonoff Basic relay switch. Our key goal of this exercise is to simulate the button and the relay itself with a D1 Mini, a switch, and a red LED, which will be acting as the relay. Before we begin this, however, let's take a quick look at the circuit design that we're going to be trying to build. Here's what we'll be configuring momentarily on the breadboard device. First, let's start off with everything on the left-hand side. So we can see here we have an LED that's hooked up to a 200 ohm current limiting resistor. That's hooked up to GPIO 12 on the ESP8266, or what is labeled as D6 on the WeMOS D1 Mini. Over on the right-hand side, we have a momentary switch that's hooked to ground. We will now configure our breadboard to match this schematic. I'll start by configuring the D3 pin, which will be hooked to the momentary push button. Following that, I'll hook up the D6 pin to the red LED in the current limiting resistor. I will fast forward to the actual hookup. So with all that configuration done, let's go ahead and do a quick test of the device to see if everything works. Let's start off by pressing the button, and if everything works out okay, the light comes on. And you'll notice that at the same time, the state as displayed on the web page also comes on, and conversely, if I press it again, it will go off. So we've just mimicked the wiring and electronics in the Sawn-Off Basic using the standard Tasmota module profile. Let's take this to the next step and manually configure Tasmota. In the second exercise, we're going to leave the breadboard configuration exactly the way it is, and instead we'll focus our attention over on the web interface and the configuration. We're going to get two things accomplished here. First, we're going to start by changing the configuration from a Sawn-Off Basic over to a generic configuration. The next step will be to configuration both pins for both the relay pin and momentary push button. So let's go ahead and get started. So as we go through and we configure the module, the first thing we need to do is change it from a Sawn-Off Basic over to a generic configuration. So let's go ahead and save that. This will take a second to reboot. Now that it's rebooted, let's go ahead and enter the configuration area once again, and let's configure the module. The first thing that we notice is that there's quite a few more pins. In fact, these are all of the pins available on the ESP8266 that can now be configured. We're only going to configure two. Let's start off by configuring the momentary push button, which is on GPIO 00 or D3. So we'll configure that as a button. And then the second pin that we have to configure is GPIO 12, which is or D6, which is the relay. So GPIO 12 bit, select that, and there we go. So both pins are now configured. So we'll go ahead and save that. And again, the device will reboot. Let's go ahead and test to make sure everything works. We'll start off by clicking the toggle button to see if it actually turns on the LED. It does. And conversely, we can turn it off. Now let's try the momentary push button. We press that, it turns on the LED, and if we press it again, it turns it off. So everything seems to work just as expected. Let's take a moment to go back to the configuration of some of the I/O pins, as I'd like to take a moment and look at some of the different options that are available. So if we look at a different device, such as GPIO 2, we can see that there's a whole myriad of different selections that one can make for a given pin. I believe there's somewhere around 25 different devices, and these can be generically categorized into input and output devices. We're going to review these in the next sessions in detail and also look at how we can do custom configurations, but suffice it to say that there's a lot of them, and they should cover most devices that we might work with. In my mind, this is the power of Tasmota. It allows us to do two key things. First off, we can take off-the-shelf consumer IoT devices and run trusted firmware on that we can control. The second is we can build our own devices without any firmware development, making it easy and fast. Our third and final step will be to design and build a more stable PCB that can be used for testing and learning Tasmota. The reason for this is that while a breadboard circuit is fine for understanding how to wire up a given component, the connections can be very unstable if you move it around. We'd like to build a reference learning PCB for testing Tasmota, knowing that the physical connections are going to be solid. Let's review the electrical schematic that we referenced a moment ago for the breadboard. Looking at the WeMOS D1 Mini, we have one analog pin and then 8 or 9 different digital pins. Let's just call it 8. Looking at my parts bin, I have the following through-hole parts handy. To start off with, I've got lots of different LEDs in different colors. I have some buzzers and beepers. I have several temperature sensors. In this case, I'm going to use a Maxim part called the DS18B20. And then I have several momentary buttons and light-dependent resistors for measuring light. Let's look at how we'll configure all of these components on the PCB, starting with a schematic view. Let's first focus on the D1 Mini pins to see how they'll be connected. To start off, we have an analog pin, and that's going to be connected to the light-dependent resistor. We then have 4 LEDs, and they'll be connected through D5 through D8 on the D1 Mini. Finally, we have 2 momentary push buttons, and we'll be connecting those to D1 and D3. We have a buzzer, which will be placed on D2, and then a temperature sensor that will be placed on D4. Let's take a look at a couple of the subcircuits that deserve extra attention, and we'll start with the light sensor. The light sensor consists of 2 components, an LDR as well as a 10K resistor configured in a voltage divider. The analog port connects between both components and will get a voltage between 0 and 3.3 volts depending upon the level of light. The other subcircuit of interest is the temperature. In this case, we're using a Maxim part, the DS18B20. This is an intelligent part that actually has a communication protocol that uses just one wire, and that wire will be connected to one of the pins. I've already laid out and manually routed all of the electrical connections from the schematic. Let's take a look at this from a 3D view perspective. This is what the resulting PCB will look like once we have it printed. We have a WeMOS D1 Mini with the USB connector on the edge of the board. Normally when I add a microprocessor to a board, I often use headers, and that's what we'll do on each of these rows of 8 pins. We also have 2 push buttons. We have a buzzer. There are 4 LEDs, our LDR, and then finally the temperature sensor. This will be a 2-layer board, and we've clearly marked each component. It should be fairly easy to solder with through-hole parts. So let's go ahead and wrap up. We started this video by mimicking a sawn-off basic with some simple circuits with an LED and a button on a WeMOS D1 Mini on a breadboard. We then configured this as a custom module profile and could see several of the options available in Tasmota. We then created a custom PCB that is a must for testing and learning Tasmota. We've already ordered this PCB from PCBWay and should have it shortly in the post. In the next few episodes, we'll show you how to assemble the PCB. We'll talk about the Tasmota pin mappings and console settings. We'll also investigate MQTT usage. Finally, we'll look at some of the rule scripts for more complex functionality. Thanks for joining me in this first pilot episode. If you found this video useful or interesting, please subscribe or like my channel. I would appreciate any comments or questions that you may have. Until the next time, this is Mark at marktroyer.tech, signing off. Now that the device has the device is now rebooted.